let's get into section 7.1 where we start talking about circles. Circles to me are terribly interesting and they're fun as well. However, they really aren't taught much. I remember teaching a geometry course in a different state and asking students what they knew about circles, what they learned in high school, and basically they hadn't learned anything. And I said, well, why not? I said, well, it wasn't covered on our exit exam, so we didn't cover it during the course. Of course, I was furious, but uh, there wasn't a whole lot I could do about it. We start section 7.1 with a great big list of terms. Now, most of these are terms that you should already know, or at least they'll be very easy for you to learn. Okay. Uh, an arc, well, let me see. First, let's make sure I've got everything working here. Nope. Back up. Let's do a skinny, and let's do blue. Okay. Okay, for an arc here, well, let's look at this circle picture I have over here. On the right, I have a circle with center O, and I have 2 points on the circle, A and B, and I have a dark curve in between those two. Well, that's going to be the arc AB. We'll denote it this way. So it is consists of 2 points on the circle and the portion of the circle that's between those 2 points. Now, we're doing what's called a closed arc, which means we include the endpoints. It is possible to have an open arc, and I guess if you had an open arc, you'd signify it that way, like you would do an open interval on a number line. Okay. Now the endpoints, well, that's obvious. A and B are the endpoints here. The endpoints of the arc is where it starts and stops. Now, if now a semicircle is an arc that uh, has endpoints of the diameter. So in this case, I have a semicircle. Now there's two semicircles here. Okay, one of them we can let's talk about the one that goes clockwise from A. Okay, I would write that. Well, if I wrote it AC, I don't know what that means. Do I mean the one clockwise from A or the one counterclockwise from A? So if I want to make sure of the arc we're talking about here, I would write this A, B, C, and put the little curve over top of it. So that means it goes from A to C through point B. So the endpoints of a semicircle are the endpoints of a diameter. Now, a minor arc is going to be something that's less than a semicircle. So in this case, AB is an example of a minor arc, BC as well. A major arc is going to be something greater than a semicircle. Okay. And for example, in this case, it would be the arc that goes from A through C to B. Okay. Now the central angle, this is an angle with a vertex at the center, and I have several central angles here. I mean, I have AOB and BOC, and AOC this way is also a central angle. And the measure of an arc equals a measure of the central angle defined by the arc. Now the book uses notation which I don't like, because they'll do something like, say, AB equals angle AOB. Okay, well, I hate that. I think that's just awful. I'm sorry they use it. If you use that notation, I'll write something nasty on your paper, but I won't take off for it because the author does. But you really should, because the arc, this is an arc. So it's a set of points on the circle. This is an angle. It is a set of points on two rays. Okay. These are sets of points. They're not equal sets of points. However, the measure of arc AB will define that to be the measure of angle AOB. Okay. This is the proper way of writing this. Okay, let's take a look at some examples here. Some of the stuff here is really, really easy. So for instance, here's a few problems from the first page of homework here. What is the measure of AOD? We've given a few angles here. AOD, well, we see that here is 43 degrees, so that means this is 43 degrees because the central angle and arc have the same measure. So AOD, well, AOC is a diameter, so AOD would be 180 degrees minus 43 degrees is 137 degrees. What is the measure of arc AD? Well, that's the same thing. Okay. Because the measure of an arc is the measure of its central angle. Okay, what's the measure of arc ADB? So this is the one that goes all the way around here. Well, let's do, well, it's going to be 180 degrees. This takes you from A to C. 65 degrees. This takes you from C to B. 245 degrees. It's pretty simple. Okay, now we're going to look at some formulas here for arc length and for area. If you have been in calculus and been working with angles there, you do everything with radians. In this course, we're doing everything with degrees, which makes some of our formulas kind of strange. They especially don't agree with the formulas you may have had in other classes, but it's the reason is we're doing degrees and not radians. Now the book has a very different approach to this. We're going to accept the following as truth. The ratio of the length of an arc to the circumference is the ratio of the measure of an angle to 360 degrees. Okay, because this is the angle. Okay, this is the angle measure that goes with this length. This is the angle measure that goes with that length. Okay. Now, if you solve for L, you get that the arc length L equals x over 360 times c, which is x over 360 times 2 pi r. Okay. What you may have, remember, if this is some angle theta in radians, then the arc length is r theta. This stuff here, x over 360 times 2 pi, this is changes degrees to radians. So this is the formula that you may have seen, and it's the formula you use in calculus. But since we're doing degrees, this is the formula we're going to have to use. Similarly, the formula for area is a little bit strange as well. The ratio of the area of some sector to the area of the entire circle is the same as this angle measure to the measure of the entire circle. Again, that's a postulate we're going to assume. We're not going to prove that. It's not really a definition. But if you multiply through by your denominator, we get a formula for the circular sector area. X over 360 times the area of a circle. If you look at your formula from calculus, if theta is your central angle in radians, then the area of a sector is 1/2 theta r squared. Okay. And here the x over 360 and the r and the pi, this is what that is. Okay. So the area of a sector is the ratio of the angle to the 360 times the area of the circle. So basically you change to radians and use the area of the circle. So let's do some examples here. Yeah, okay. Here I have a circle. Okay. Segment AC is a diameter. BC is 115 degrees. Okay, so let's write that in here. This is 115 degrees. Actually, that means this is 115 degrees. Okay. Angle DOC is 25 degrees. Well, I can't fit that in there. This is 25. And OA is 8. OA is 8. So this amount is 8. This is then the radius. Okay, find the lengths of BC and AD, arcs BC and arc AD, and round to the nearest hundredth. Okay, so the length of BC is, well, the angle that forms BC is 115 degrees. You divide that by 360, and you multiply this by the 2 pi r. Okay, make sure I got my formula right. Okay, it's this guy here. X over 360 times 2 pi r. So, and you want to round this to the nearest hundredth. So this is about, I've got this right, 16.06 centimeters. Oh, by the way, they have a really big mistake up here. It should be, okay, when you put a bar over OA, you're talking about the line segment, which is a set of points. If you don't put a bar over it, you're talking about the length of the line segment. So 8 centimeters is not a line segment. 8 centimeters is the length of the line segment. Okay, so the length of the arc BC is about 16.06 centimeters. The length of AD, okay, well, what is the angle here? Okay, the angle AOD, oops, I'm going to make the mistake here. The measure of angle AOD is 180 degrees minus 25 degrees, which is 155 degrees. So the length of AD then is the angle measure over the measure of an angle of a whole circle times the circumference of the circle, which is 2 pi times 8. And that's about, if I've got this right, 21.64 centimeters. Okay, now let's find the area of this little bitty piece of pie here, this little bitty wedge. So the area of the sector is going to be the angle divided by the angle of the whole circle times the area of the whole circle, which is pi r squared. Okay. And punch that into your calculator and round it off. 13.96 square centimeters. Okay, pretty straightforward stuff there. Now we come to the main theorem in this section called the inscribed angle theorem. Now an inscribed angle is an angle with the vertex on the circle. Okay, so the vertex is a point on the circle, and it intersects the circle in two other places. I mean, each side of the angle intersects the circle in other points. Otherwise, I'm not saying this very well. This is not an inscribed angle because this side does not intersect the circle. Okay. This is not an inscribed angle because the vertex isn't on the circle. Okay. All right. And the inscribed angle theorem says that the measure of angle ABC is 1/2 the measure of arc length AC. Now, let's make sure we understand what that means here. The measure of the arc length is, if here's the center, remember the measure of the arc length, that's not very good. It is the measure of the central angle that determines the arc. So this is, what I mean is, I shouldn't say measures in front of this. This is going to be 1/2 the measure of the central angle. Let me write that better. Where O is the center of the circle, it's 1/2 the measure of AOC. Now this has three different cases, and I will prove all three of them. The book proves one of them and puts the other two in the exercises. I've redrawn things a little bit here, but the first case is one side of the inscribed angle is a diameter, so one side passes through the center. And that one's pretty easy. Another case is that the center of the circle is actually completely outside, exterior of the angle. Okay. And the third case is the center of the circle is interior of the angle. Okay. Okay, so let's work with case one here. And I'm going to be drawing a bunch of lines. Let's pick a different color here. Okay. And again, my proof, I may leave out a few steps here, I don't know. So the first thing I want to do on case number one is I want to draw this angle, this line. Okay. So here's my, let's draw OA. And our definition here, the measure of the arc length AC is equal to the measure of angle AOC. That's the definition of arc length measure. Now, let's note that that OA is congruent to OB because both of these things are the radii of a circle. I mean, this is a circle, so the radius is the same. So this side and this side are the same. And this is a triangle here. Triangle ABC, ABO, excuse me, is isosceles. And if you've got an isosceles triangle, the angles opposite the congruent sides are congruent. So angle OAB is congruent to angle OBA. Or let's call that ABO. Anyway, let's rename these. is isosceles, and so angle ABO is congruent to angle BAO. Okay, so those two guys are congruent. They're the same measure. All right, now we're interested in angle AOC. We're interested in this angle down here. Angle AOC is external. It's an external angle for triangle AOB. So what that means is the measure of angle AOC is equal to what you get when you add up these two angles. The measure of angle ABO plus the measure of angle BAO. But ABO and BAO are the same measure. Okay, they're congruent angles. So this is 2 times the measure of angle ABO. Now that's just another name for 2 times the measure of angle ABC. Okay. So and of course this the AOC is the measure of arc AC. Take 1/2 of both sides. Oops, wrong thing. Take 1/2 of both sides. 1/2 the measure of arc AC equals the measure of angle ABC, which is what I wanted to prove in this case. Okay. So if one side of the inscribed angle goes through the center, so one side is the diameter, it's a pretty straightforward thing, an argument that it's an external angle argument for the triangle that's formed. Okay, case 2. In this case, the center is exterior to angle ABC. Okay. What I want to do is I want to use what I just did. So this is going to be a little bit different. I'm going to stick an extra line segment in there. So the proof on this one is draw a diameter. BD. Okay. So let's draw a diameter here. Okay. And let's draw OC as well. I think I want that one. Yeah. Let's draw this line segment as well. Okay, let's see what we have here. Now the measure of arc AC equals the measure of arc AD minus the measure of arc CD. Right? So it's the big arc here minus this little piece will give me AC. All right. Now, AD. So we're looking at big from A to D, okay, and the measure of arc AD, oops, looking at the wrong thing here. I'm doing wrong. I'm looking at the wrong part. I haven't said anything wrong yet. Okay. I'm getting ready to because I'm looking at the wrong part of my page here. Okay. Now, we're interested in angle ABC. The measure of angle ABC is the measure of angle ABD minus the measure of angle CBD, right? So it's ABD minus it, so it's this big angle minus that little angle. Okay. Now, the measure of angle ABD, so I'm talking about this side, is it is an inscribed angle where one side goes through the center, or one side is a diameter. So I can use the previous page. This is an inscribed angle where one side goes through the diameter. I know that the theorem works for that. So that's 1/2 the measure of the arc, AD. The measure of CBD, this is an inscribed angle where one side goes through the diameter. I mean, one side goes through the center, so one side is a diameter. And I know that by the previous thing that the measure of angle CBD is 1/2 the measure of the arc it intercepts, CD. So this is 1/2 the measure of arc AD minus the measure of arc CD. But AD minus CD is the measure of arc AC. So it works for that one as well. And the last one is a similar sort of problem. And this is the one that's done in the book. So let's start out the very same way. Draw a diameter. Let's draw a diameter BD. So I'm going to need a line from B that goes through the origin. So this is a point D. And now it's the same, actually it's the very same thing as the previous one, except put a plus in here where I have a minus. Okay. The measure of angle ABC is the measure of angle ABD plus the measure of angle DBC. Okay. So it's this angle plus this angle. Okay. And if angle ABD is an inscribed angle where one side is a diameter, so I know from what I did in case 1 that the inscribed angle theorem means that's 1/2 the measure of the arc length AD, measure arc AD, and the measure of angle DBC, well, it is an inscribed angle where one side is a diameter, and so by case 1, I know that that's 1/2 the measure of the arc DC. Okay. So this is 1/2 the measure of AD arc plus the measure of DC arc, but arc measures add up. So this is 1/2 the measure of arc AC. Okay, so that that proves the third case as well. Now, If you look in other books, they may not call this inscribed angle theorem. As a matter of fact, I have one geometry book where they call this the Star Trek theorem. Okay. Because what they've done is they've taken this last case and draw the radius from O to A and O to C and said, oh, we get something that looks like this. And that looks kind of like the Star Trek emblem. So it's also called the Star Trek theorem. Okay, a few corollaries in here. Very, very simple. So I'm not going to work too hard on proving these. Inscribed angles that intercept the same arc are congruent, or congruent arcs are congruent. Okay, well, that's pretty clear. Because the measure of angle CAD is going to be 1/2 the measure of arc CD, and the measure of angle DBC is going to be 1/2 the measure of arc DC because of the previous theorem. These two things are the same, so these two things are the same. And so they should put this. Corollary 7.3 is one that turns out to be a very interesting one, a very useful one. An angle inscribed in a semicircle is a right angle, and vice versa. In other words, if you draw a circle, let me see if I can draw a circle here. Let me start with a point here. Okay. If you draw a circle, and draw any diameter of that circle, pick any point on the circle. Okay. I just drew a right triangle. Because this is guaranteed to be a right angle. The proof of this, I'm not going to go through, but if you have a right angle, okay, and it's an inscribed right angle, then it's going to, that's going to be half the measure of the arc it inscribes. So if this is 90 degrees, it's going to be half of 180 degrees. If you have a 180 degree arc, then the angle that inscribes it has to be 90 degrees. So very, very straightforward sort of thing here. Okay, let me scoot this stuff up where we can work on it a little better. Okay. All right, exercises 19 through 30. We have this figure drawn, and some of these are very, very simple here. Okay, name an angle that intercepts the arc DA and indicate whether the angle is an inscribed angle, a central angle, or neither. Well, DA is this arc down here at the bottom. So the angle we're looking at here is angle AED. At least there are other angles that inscribe it, but that's the only one that's drawn in this case. Now, this is not inscribed. Okay, I think I said something wrong just then. There are some other angles that intercept arc DA, but this is the only one that's drawn. Okay. Since the vertex E is not on the circle, it is not inscribed. Okay. Now, E looks like it might be close to the center, but nowhere in this do they say E is the center. So if E is not the center, then it is not central. Okay. So I would say in this case it's neither. Since they never tell you what that E is the center, we can say it's neither. Okay, and number 30. What's the measure of arc BDA? So we're looking at BDA. Well, That's okay. Well, I thought this was going to be harder than that. Okay. Arc BDA, 180 degrees. Okay, because BA is a diameter. Nope, excuse me. Wrong, wrong. Nope, I don't know BA is a diameter. What is the measure of arc BDA? Well, what's the measure of okay, the picture is misleading. Nowhere did they say E was the center. So I don't know. So the measure of arc BDA is going to be 80 degrees plus the measure of AD. No. Okay. I'm still making it too hard. Okay, let's do it this way. It's 360 degrees minus the measure of arc BCA. So, so this means this is 360 minus 70 minus 110, excuse me, minus 70 minus 100. Okay, so 360 minus 170, that's 190 degrees. Okay, that's the easiest way to do it. I did it some other stupid way on my notes, and that's why I'm fumbling it here. Okay, a few more. Here's one that's just terribly easy. Number 38. If arc BC is 38 degrees, so this is 38 degrees, then what's AB? Well, AC is a diameter, so the measure of AB is going to be 180 degrees minus 38 degrees is 142 degrees. Now, BC does not look like a 38 degree angle. I mean, this does not look like a 38 degree angle, but if they say this is 38 degrees, then it's 38 degrees. Okay, now 45. We come to a kind of complicated one, and there's all sorts of ways to do this, and I'm not sure I've got the shortest method of doing this. Uh, Let me put in a few numbers here. Okay, AE is 120 degrees, so that's this arc, and O is going to be the center. Okay, we name the circle by the center. Okay, so let me get a little extra space here. Okay. So if AE is 120 degrees, then this is 120 degrees. Okay, which means this is 120 degrees. Okay, and if this is 120, this is 60 because they form a straight line there, and this would have to be 60. Okay. Let's see, I'm getting carried away here. Let's find a few other things. Find the angles, 5 angles of a pentagon here. Okay, now, angle BAE. This angle here, that is a right angle. Why? Because it inscribes a semicircle. The same thing for angle AED. and scribe semicircle. So that's a right angle, and that's a right angle. Okay, let me draw a line in here, which might help. Okay. Let's draw OC. And what we know is that CD is a 42-degree angle. Tell you what, I want to get rid of something here. Let me see if I can. Yeah, let's get this off. CD arc is a 42-degree arc. So that means this angle is 42 degrees. And let's go ahead and get this angle here. So angle BOC is going to be what? It's going to be 180 degrees minus 60 minus 42. Okay. Right. So this is 120 minus 42. That means it's 78. Okay, so I'm just about ready here. Okay, here's two of them right there. So I got those two. I need three more, and they're going to run real fast here. So this is 78 degrees. All right, let's call these X. Let's call that X. Now, I'm marking in here. This is a circle. So every one of these little segments that goes from O to the circle, all are the same length. So every little triangle I've got drawn here that's got a vertex of circle, they're all isosceles. So triangle BOC is isosceles. So that means those two sides are the same. So if I add X and 78, 2X plus 78, I should get 180 degrees, right? So 2X is 102 degrees, X is 51. Okay. Triangle COD is isosceles. Okay, for the same reason. So those two angles are going to be the same. Let's not call them X. So if I add those two together, then the 42-degree angle in the center, I should get 180 degrees, right? So 2Y is going to be 180 minus 42 is 138. So Y equals 69 degrees. Okay. So I can go ahead now and get the measure of angle BCD is 51 plus 69, 120 degrees. Okay. Now I just have two more to get. What's this angle? Okay, of course that's going to be the same as that one. Well, we can do this several ways, but since triangle DOE is isosceles, okay, then 2 times question mark plus 60 is 180. So 2 question marks is 120. So it's all 60 degrees. So this is 60. This is 60. So the measure of angle, let's do ABC, is 60 degrees plus X. And the measure of angle CDE is Y, which is 69 degrees, plus the question mark, which is 60 degrees, which is 129 degrees. Okay, there they all are. Okay, finally, I've got one proof to do here. I think you need to think about this figure when you're working problem number 50. At least when I was working number 50, this particular figure came to mind. In other words, you may want to draw some diagonals on number 50. I don't know. But think about this. When you're working on number 50, come back and look at what I've got down here for number 48. Okay, so in this figure, AB is parallel to CD, and you want to prove that CED and AEB are isosceles triangles. Now, I don't know where the center of the circle is. It really doesn't matter. Okay, so let's use some of the tools we got in this section. Angle BAC and angle BDC both intercept arc BC. And they're in, okay, they are inscribed angles. So that means that angle BAC is congruent to angle BDC. Oops. So this and this are the same. Okay, next step. Angle BAC and angle ACD are alternate interior angles formed by parallel lines. Okay, so they are angle BAC is congruent to angle ACD. So this angle and this angle are congruent. Hence angle, we're just renaming them now, EDC is congruent to angle ECD. So triangle DEC is isosceles. So we had this theorem back there when you have a triangle where two angles are congruent, then the opposite sides are congruent, so it's going to be an isosceles triangle. Okay, now one of the things I haven't noticed, I haven't done yet too, is that angle ABD is congruent to angle BDC. So this angle and this angle are congruent because they are alternate interior angles. They too are alternate interior angles formed by these things. So let's see, ABD, where do I appear? So angle ABD then is congruent to BD is congruent to angle BAC. Yeah. Okay. This is just angle ABE is congruent to angle BAE. So triangle AEB isosceles, you've got a triangle where two angles are congruent, so the opposite two sides are congruent, so it's an isosceles triangle. Okay, so I've left some of the reasons out, but I think we've got, there's all the important steps there. Okay, so we'll do some more with circles, but it'll be in the next, it won't be due this week. Yes, 7-2, 3 and 4 homework will be due next week, but this should get you through section 7-1 stuff. Good luck.